So previously, we've discussed the idea of a Taylor polynomial. So a Taylor polynomial for f of x about the point x equals a is the polynomial, which is the sum from k equals 0 to n. And then we're going to take the kth derivative at x equals a, divide that by k factorial, and multiply it by x minus a to the k power. And the basic idea behind this Taylor polynomial is that f of a is equal to the polynomial evaluated at x equals a, and then every derivative of f at x equals a matches every derivative of the polynomial at x equals a. So the kth derivative, so all derivatives of f of x, so those are fk of a, match all derivatives of the polynomial at x equals a. So that's p sub n, the kth derivative at x equals a. And then what we saw was that these polynomials make great approximations of f of x. And if we increase the order of the polynomial, so if we increase the number of terms in the polynomial, then we get better approximations for f of x. In the previous activity, we also saw that these polynomials matched the first n terms of series for various functions. So it would be natural to extend the idea of the Taylor polynomial to an infinite series, which we're going to call a Taylor series. And so instead of the polynomial, which is a finite number of terms, being an approximation for the function f of x, then the infinite series, that's the Taylor series for f of x, will actually equal f of x. Okay, so in this case, we'd say that f of x is equal to the infinite polynomial, where you sum from k equals 0 to infinity, fk of a over k factorial times x minus a to the k power. Now on Monday and Tuesday, we're going to talk about Taylor's theorem, and Taylor's theorem tells us why the function is actually equal to the infinite series. For now, I'm going to ask that you accept that it equals the infinite series, but it does as long as the series converges. So if we can show that the series converges for various values of x, then the Taylor polynomial will converge to f of x for those values of x. So this is best illustrated by using an example. So we're going to find the Taylor series about the point x equals 2 for a function. The function is going to be 1 over 1 minus x. Now, 1 over 1 minus x, we're quite familiar with, right? That's the sum of a geometric series, but that's the sum of a geometric series that's centered at x equals 0. Now I want to find a Taylor series about the point x equals 2. So my function is going to be f of x, and that function is 1 over 1 minus x. Another way to write that is 1 minus x to the negative 1 power. And then what I'm going to do is I'm going to evaluate that at 2. So that's going to be 1 over 1 minus 2. And of course, that's going to be negative 1. And then I'm going to find the derivative, which is actually negative 1 minus x to the negative 2 power. That's times a negative 1. And so using the chain rule, I get that -1 there. I'm going to simplify because negative times the -1 is going to give me a positive. And so the derivative at 2 is actually 1 over 1 minus 2 squared. That's a -1 squared, so that's 1. The second derivative of x is actually going to be -2 times 1 minus x to the -3 power. That's times a -1, so that becomes a plus. So the second derivative at 2 is 1 over 1 minus 2 cubed. That's a -1 cubed, so that's a negative, sorry, it's 2 over 1 minus 2 cubed. So that's 2 over -1 cubed. That gives me a -2. The third derivative is going to be a -3 times 2 times 1 minus x to the -4 times a -1, so that becomes positive. So the third derivative at 2 is actually 3 times 2 over 1 minus 2 to the 4th. 1 minus 2 to the 4th, that's -1 to the 4th, or 1. So this becomes just 3 times 2. And then I'm going to do a fourth derivative. Fourth derivative at x is actually -4 times 3 times 2 times 1 minus x to the -5 power. And that fourth derivative at 2 is actually going to be -4 times 3 times 2. Oh, sorry, that's a positive 4 times 3 times 2 because of the chain rule again. And then that's a 1 minus 2 to the 5th power on the bottom. So 1 minus 2 to the 5th power, that's going to be -1. So I'm going to get -4 times 3 times 2. So once you take a bunch of derivatives, you can establish a pattern. What is the nth derivative? The nth derivative in this case looks like, well, the fourth derivative had 4 times 3 times 2. The third derivative had 3 times 2. The second derivative was 2. So this looks like n factorial times 1 minus x to the -n plus 1. And so the nth derivative at 2 is actually going to be, you can see that it alternates. So we're going to do -1 to the n plus 1 because it starts with a -1, then it goes positive, negative, positive, negative. And then that's times n factorial. And so once you've taken enough derivatives, maybe 3 or 4, you can establish a pattern for the derivatives. And now, once we have the pattern for the derivatives, we're going to plug that into our series formula. I will notice that I did use k's in my series formula, so I'm going to just change these to k's real quick. So this is the kth derivative. That's going to be a k factorial. This is not necessary for you to do, but I'm going to do it so that I'm consistent. So this is going to be the kth derivative at 2, and that's -1 to the k plus 1 times k factorial. Okay, so I'm going to plug that into the series formula. I'm going to try not to hide the series formula for the moment. So, so that tells me that f of x in this case is equal to the sum from k equals 0 to infinity of the kth derivative at a, so that's -1 to the k plus 1 times k factorial over k factorial times x minus a is 2 to the k power. So notice again, you always find the Taylor series around x equals a. This time we're finding it about x equals 2. So that tells me that a is 2, right? X is a, so in that sense. Okay, so that gives me the Taylor series near x equals 2, you can simplify this because the k factorials cancel. And so my series looks like the sum from k equals 0 to infinity of -1 to the k plus 1 times x minus 2 to the k power. And so that that series exactly equals f of x as long as x is within the radius of convergence. So you would have to then use the ratio test to show where this converges. It should be fairly simple to use the ratio test to show that this converges for x minus 2 less than 1 in absolute value. So the radius of convergence in this case is 1. That would be fairly simple to show. It would be a very simple problem. So this is a good, or this is actually equal, f of x is equal to the infinite series when x minus 2 in absolute value is less than 1. So when you're within 1 of 2. And the polynomials themselves are good approximations when you're within that radius of convergence. So I'm actually going to plot the series and I'm going to plot the function. So here's the function 1 over 1 minus x. I'm interested right here around x equals 2. Okay, so I'm interested in that. I've plotted the first 2 terms of this series to start. That's the linear approximation. So that's just -1 plus x minus 2. Okay. And then I'm going to plot more terms. So if I'm adding, as I add more terms, I want you to see that the Taylor polynomials start to converge to the function. I get better and better approximations as I add more terms. When I'm up to 20 terms there, it looks like I have a really good approximation on the interval from 1 to 3. And that's exactly what I expected because the radius of convergence here is 1. So this series converges between 1 and 3. So so that's a good approximation there between 1 and 3. Okay, so we're gonna move on. So you can see my Taylor series converges between 1 and 3. So now I've found essentially that I can rewrite 1 over 1 minus x as this this polynomial near x equals 2. Okay, and notice it's different than what I got when I had the geometric series, okay, which was centered at x equals 0. Now, it turns out that we could have gotten this series another way, okay, because it does look like a geometric series. And I want you to see that because then you'll see how the answers are the same. So it turns out that f of x is 1 over 1 minus x. It turns out that's the same thing as -1 over x minus 1. Seems silly to do that, but you'll see in a moment why I'm going to do it. This is -1 over actually x minus 2 plus 1. So -2 plus 1 is -1. So that's another way to write it. So I can rewrite this series as -1 over, I'm going to put the 1 on the left, and this is 1 minus a negative x minus 2. And I wrote it that way because now this looks like a geometric series. It looks like a number divided by 1 minus something, say, in this box. So I can actually rewrite this as a geometric series. It's negative the sum from k equals 0 to infinity of negative x minus 2 all to the k power. Well, that is the sum from k equals 0 to infinity. I'm going to distribute out that k power, so I'm going to get -1 to the k, but I'm also going to use that negative sign right there. I'm going to put that in as well. So this is -1 to the k plus 1, and then it's x minus 2 to the k, and wow, that is the same series. Okay, that's the same series as the Taylor series that we saw. And then using geometric series, we know that that must converge when r is less than 1. So that's the same thing as absolute value of x minus 2 less than 1. Okay, so you can get this Taylor series in two ways. You can use geometric series as long as it's centered at the right point. I needed to center this at x equals 2, or you can do it using derivatives. Okay, so that's my first example of Taylor series. And so you'll have some problems with some functions where you have to find a Taylor series for a function centered at a point x equals a. There's some very special Taylor series that are used over and over again. They are Taylor series that are centered at x equals 0. And for some reason, we call Taylor series centered at x equals 0 Maclaurin series. You won't hear me say that name a lot, because I kind of feel like Taylor came up with this idea for Taylor series, and he has all the generality of Taylor series when it's centered at x equals a. So I asked myself, why was this specific series when x equals 0 named after Maclaurin? It doesn't seem like he added very much to it. I feel like he cheaply got his name like on this series. Maybe he paid for the naming rights for these series, like companies pay for the naming rights at various ballparks. So I don't know, but Maclaurin gets his name often on series that are centered around x equals 0. And these series that are centered around x equals 0, they're used quite often. So I want to show you some very specific series centered at x equals 0. I'm going to start with e to the x. I'm going to call that my f of x. And I'm going to note that every derivative of e to the x is e to the x. And so if I want to center my series at 0, every derivative at 0 is e to the 0. And so we can say that e to the x, using the Taylor series formula, should be the sum from k equals 0 to infinity of the kth derivative at 0 over k factorial times x minus 0 to the k power. That is the Taylor series formula. So I'm going to write this as e to the x is, well, all the derivatives at 0 are 1. So this is 1 over k factorial x to the k. And so e to the x is actually equal to this series. The series looks like 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... Okay, so that is the series that can represent e to the x. Now, at least in class and for homework, you showed that this series converges for all x. So this series has an infinite radius of convergence. So, so we can use Taylor polynomials to approximate e to the x for any x. Doesn't matter how large x is. Of course, you'll need more terms the larger that x is. And I believe I also showed this converging for you guys at some point. So I'm going to go ahead and not show the convergence right now. So that is a simple Taylor series to find. Let's try sine x. So my function f of x is sine of x. And then I'm going to find derivatives at 0. So f of 0 is the sine of 0, which is 0. The derivative of sine is cosine. And so the derivative at 0 is cosine of 0, which is 1. The second derivative is negative sine of x, just taking another derivative. So the second derivative at 0 is negative sine of 0, also known as 0. The third derivative at x is going to be negative cosine x, just taking another derivative. So the third derivative at 0 is going to be negative cosine of 0. So that's a -1. And then the fourth derivative of x is going to be, the derivative of negative cosine x is sine x. And so the fourth derivative at 0 is negative sine of 0, which is 0. And notice that we actually get back to sine x. So that means that there's a pattern that's going to start to form here, because the fifth derivative is cosine, then the next derivative is negative sine, then negative cosine, then sine. And so these derivatives are going to cycle in this pattern of 4. So you start with f of 0 is 0, and then the next derivative is 1, and then 0, then -1, then 0, then 1, then 0, then -1, then 0, then 1, then 0, then -1, then 0. So what I'm going to do is I'm going to write out what the sine x series looks like. The very first term is 0. I'm going to use this pattern here. So the pattern that you've seen here, that pattern is what I'm going to use to establish what the series for sine x is. Okay. So the first term is 0. The next term is a 1 over 1 factorial x to the 1 power. That is also known as x. The next term is 0. Then we're going to get a -1 over 3 factorial x cubed. And then the next term is 0. And then we get a +1 over 5 factorial x to the 5th. The next term is 0. Then we get a -1 over 7 factorial x to the 7th. The next term is 0. And then this pattern continues on. And so we can write the series for sine x. It's kind of easier to write it having seen the first several terms first. It is an alternating -1 to the k. And then we want odd terms in the denominator. So we're going to get 2k plus 1 factorial in the denominator, x to the 2k plus 1. And that series, if you, because it's kind of similar to the e to the x series, it has many of the same terms as the e to the x series, except for it's missing kind of the odd terms, and it alternates where the e to the x series does not alternate. But that you can show using the ratio test converges for all x, for x between -infinity and infinity. And so this series is often used to approximate sine x. So I'm going to show you a graph of that. So don't worry, this will come back so you can look at it again. But I want to show you a graph of that. So just give me a second to find my Taylor series for sine of x on here. There it is. Okay, great. So what you see here is sine of x, and then the series for sine of x. And right now I have the very first term plotted. So the very first term is sine of x is approximately x. And so you have a linear approximation here. And the linear approximation is a pretty good approximation when x is small. So you'll often hear people say, especially in physics classes, that when x is small, sine of x is approximately x, or sine of theta is approximately theta. So this is called the small angle approximation. It's used often, but that is the first term, and it's a good approximation to start for sine of x. But as you increase the number of terms, so there's the x cubed over 3 factorial term, x to the 4th over x to the 5th over 5 factorial term, x to the 7th over 7 factorial term. If I keep increasing the number of terms, look at how the series starts to approximate. With 10 terms, I've almost got the whole interval between -10 and 10 there with 10 terms. If I keep going, then I can increase the number of terms and I just get more of sine of x. And so you can see why is if I keep adding more terms, I'm going to get better and better approximations of sine of x, and they're going to be able to expand out for x between minus infinity and infinity. So 20 terms gives me a really good approximation of sine of x, say between minus 15 and 15. So that's how these series work. You can see them converging to the function. Okay, so we're going to do one more. This is actually a function we found a series before, which is natural log of 1 plus x, but I want to do this as a Taylor series. So here we have f of x is the natural log of 1 plus x. The derivative, or sorry, f of 0 in this case is going to be natural log of 1 plus 0. So that's natural log of 1 or 0. So the very first term in this series is actually going to be 0. The derivative is 1 over 1 plus x. So the derivative at 0 is 1 over 1 plus 0, which is 1. 1 over 1 plus x, that's like 1 plus x to the negative 1 power. A little easier to take the derivative of that. The second derivative is going to be negative 1 plus x to the negative 2. So the second derivative at 0 is going to be negative 1 over 1 plus 0 squared. That's negative 1. The third derivative is going to be 2 times 1 plus x to the negative 3. So the third derivative at 0 is 2 over 1 plus x cubed, 1 plus 0 cubed. So that's 2. And then I'm going to do one more. The fourth derivative at x is going to be negative 3 times 2 times 1 plus x to the negative 4. So the fourth derivative at 0 is going to be negative 3 times 2 over 1 plus 0 to the fourth. So that's a negative 3 times 2. That should be enough to establish the pattern so that the kth derivative at x is, well, for the fourth derivative, I got a 3 factorial. And for the third derivative, I got a 2 factorial. So this is going to be a negative 1 to the k plus 1 times k minus 1 factorial, 1 plus x to the negative k. And so if I'm looking at that kth derivative at 0, that's going to be, looking at this, it's going to be negative 1 to the k plus 1 times k minus 1 factorial. So when you're establishing the pattern, you really only need to establish the pattern at x equals 0. But you see that every time I find one of these series, I start to make a chart like this. And I really recommend that you make charts like this. It will help you find these series. I'm going to put this into the formula for natural log of 1 plus x, or for the Taylor series. So we have that f of x is actually equal to the sum from k equals 0 to infinity of, this is going to be negative 1 to the k plus 1 times k minus 1 factorial over k factorial. And this is going to be x to the k power. We can simplify because k minus 1 factorial over k factorial is just k. Okay, so we're thinking about k factorial as being k times k minus 1 factorial. And so it's negative 1 to the k plus 1 over k, x to the k. I'm going to write out a few terms so that we can see what it looks like. It looks like x minus x squared over 2 plus x cubed over 3. That's a very, very good point. I've made a mistake. Notice that the very first term was 0. So I should have started my series not at not at 0, but at 1. So my series starts actually at 1. Otherwise, so the 0 just doesn't fit the pattern. Okay, so my series actually starts at 1. Okay, so adding a few more terms, we get plus x to the 4th over 4 minus x to the 5th over 5, etc. So that's what the series looks like. Now, if you use the ratio test, and you've actually done this one before as well, but if you use the ratio test, this actually converges not for all x, but only for x between -1 and 1, including 1. So we've actually shown that one before, because we actually found this series using geometric series, doing integrating term by term. So this actually matches the answers that we had before. So that'll so this series only converges between -1 and 1. I think I can quickly show you Taylor expansion for that. I really hope that I have this one. Yep, I do. So here we have the series. Let's see. So I'm just looking. I'm looking here. I don't see the series. I'm not sure why I don't see the series. I'm going to delete the x to the n and then see what happens here. Oh, it's because I started it at 0, of course. So you can see, you can't just always assume it starts at 0. There we go, much better. Okay, so there's the linear approximation for natural log 1 plus x. As I increase the number of terms, notice that it converges between -1 and 1, because the radius of convergence is between -1 and 1. It does not converge outside of -1 to 1 there. Okay, so there you go. That is the convergence of the Taylor series for natural log of 1 plus x. Okay. So, so these series pop up often enough that there are just some that you really should know or be able to refer to often. So they are e to the x, we just found, sine of x, which we just found, cosine of x. Cosine of x is actually interesting because you can take sine of x and then take the derivative term by term. And since the derivative of sine x is cosine x, then the derivative term by term of sine x is the series for cosine x. And so cosine x is actually one you're going to do from homework for homework. So you're going to want to go back to this technique and basically establish the pattern for cosine x and do it by hand for homework. But that's one of your homework problems. But cosine x, very important. Natural log 1 plus x we've done. Arctan of x we found in a previous class, so that one's very, very useful. And finally, this special case is actually very, very useful. That is, that special case is the geometric series, which you've shown before. Okay, so those are all the series that are important. These are the important Taylor series that are centered around x equals 0, and we'll be using them a lot. So what we're going to do with them in particular is we can use these series that we already know to construct other series. Sometimes ways that you can do that is by taking derivatives, like the derivative of sine x is cosine x. But we can also think about these series in a slightly different way. So when I think of sine of x, I don't have to think about it as just being sine of x. I can think about it as being sine of anything inside this box. And then the series for the sign of something inside that box is actually, it's box minus box cubed over 3 factorial plus anything inside that box to the 5th over 5 factorial minus anything inside that box x to the 7th power over 7 factorial. So you can think about it as some sort of box to the 2k plus 1. And so what I can do is I can substitute things like sine of 2x. And so what's inside my box there is the sine of 2x. And so what is the series for the sine of 2x? Well, it's going to be, I'll put it in green for fun here. So let me do the formula here. So it's a sum from k equals 0 to infinity of -1 to the k plus, or -1 to the k over 2k plus 1 factorial, and then you put in something in the box to the 2k plus 1 power. And what that ends up equaling is essentially that box minus the box cubed over 3 factorial plus the box to the 5th over 5 factorial minus the box to the 7th over 7 factorial, etc. But the thing that we want to stick in this box is actually going to be 2x. So everywhere I see the box, I'm going to put in a 2x. And so this series is actually going to look like the sum from k equals 0 to infinity of -1 to the k over 2k plus 1 factorial. And then I have a 2 to the 2k plus 1 times x to the 2k plus 1. So I'm going to factor that out. This looks like, or expand that out. This looks like 2x minus, and then 2 cubed x cubed, so 8x cubed over 3 factorial, plus 2 to the 5th, so 32x to the 5th over 5 factorial, minus 2 to the 7th, so 128x to the 7th over 7 factorial plus ... And so now we have that the series for sine of 2x, just by using the series for sine of x. So I didn't have to find derivatives again. I didn't have to do any of that. I could use the series for sine of 2x. I could find the series for sine of 2x just by using the series for sine of x. And this actually converges for all x between all 2x's between minus infinity and infinity. But if 2x is between minus infinity and infinity, then certainly x is between minus infinity and infinity. So that kind of works out really, really nicely. We found the series for 1 natural log of 1 plus a box. So we can find that series. That's the sum from k equals 1 to infinity of -1 to the k plus 1 over k. And then it would be times the box to the k power. The terms, they kind of look like box minus box squared over 2 plus box cubed over 3 minus box to the 4th over 4 plus ... And so here we would want to put our x squared over 2 in the box. So here I'm going to put x squared over 2 inside these boxes. And we can expand these out to find the series. So this is actually going to look like the sum from k equals 1 to infinity of -1 to the k plus 1 over k. in fact, it's going to be over 2 to the k times k, and then it would be x to the 2k power. And so this series looks like x squared over 2 minus x squared squared is x to the 4th. 2 squared is 4 times 2 gives me 8, plus x squared cubed is x to the 6th. Then I have a 2 cubed times 3, so that's 24, minus x to the 8th over 2 to the 4th times 4, so that's 64, plus dot, 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 dot. Okay, and so now I've found the series for natural log of 1 plus x squared over 2 because I knew the series for natural log of 1 plus x. So what does this converge for? This converges for, well, what's in the box has to be less than 1 in absolute value. That's was the radius of convergence, which was 1. So that converges for x squared less than 2. And so that converges for absolute value of x less than square root of 2. Okay, so that is the radius of convergence, which is the square root of 2. Okay. I'm going to do one more real quick, so hang in there with me. This is x squared times e to the 3x. So this is going to be x squared times the sum from k equals 0 to infinity. The series for e to the 3x is actually, I'll put it in green one more time. It's box to the k power over k factorial. And so what we're going to do is we're going to put the 3x in that box. I'm not going to write out the terms this time. This is just going to be x squared times the sum from k equals 0 to infinity of 3 to the k x to the k over k factorial. And then I'm going to write it one more time as the sum from k equals 0 to infinity of 3 to the k over k factorial, and then that's x to the k plus 2. And that will converge for x between minus infinity and infinity. So essentially, if I already know the series for e to the x, then I can find the series for e to the 3x, and then I can multiply that by x squared, and now I have that series for x squared e to the 3x.